let's just see. Boop, boop. Nice. That is so bright. Oh, this isn't on.
You're good. You're on the right connected. So I think we're missing 2 people, but let's get started anyway since we're over behind.
Okay, cool. Great. So today I'm going to talk about library structure 3, which is essentially how you can control movement in Rosetta, some of the kinematics in more detail than we've looked at. And then after this, we're going to be doing a lab on the FoldTree where you'll get hands-on on some of the really fundamental and tweakable kinematics that you have access to in Rosetta. So a brief outline of what we're going to do today, which is there we go. The first thing we're going to talk about is packing sidechains with Rosetta. A lot of you may have done some of this before. We're just going to briefly introduce packing, some of the core classes that are involved, and how you can control packing. And then we're going to do an introduction into movement and internal coordinates. We've gotten a little of this already. We're going to go into a little bit more detail about the atom tree, and I'll just touch on the FoldTree because we have an entire lab dedicated to it. And then degrees of freedom and controlling degrees of freedom is another thing we're going to talk about, which leads us to applying and controlling movement, which is done by the MoveMap. And then we'll touch on a couple common ways you can control movement in Rosetta. And so this is meant to be kind of a practically useful thing. A lot of this stuff is things you're going to be using on a regular basis when you're writing protocols. So hopefully you come back to it and get some use out of it. So a lot of you probably know this, but when we refer to packing in Rosetta, we're talking about making amino acid or Rotamer substitutions to a fixed backbone. And so a Rotamer is a rotational isomer. And so here we have this histidine, and we're putting in a glutamine. But a Rotamer defines a conformation. So you can have multiple Rotamers for the same amino acid. So this could easily be another histidine in a different spot, and that would be another Rotamer. All right. And so where do we get our Rotamers in Rosetta? They come from the Dumbrack lab, and they had previously come from the Mayo lab. I don't think we use the Mayo conformational Rotamers anymore. So it's almost entirely from the Dumbrack lab, and these have ideal bond lengths and angles. Is that right, Andrew? We don't use the Mayo conformers anymore? Yeah, that's what I thought. So really they come from the Dumbrack lab. And they can also come from your PDB. If you give an input PDB to Rosetta, you can say the current conformation of the sidechains I want to add as a Rotamer to the Rotamer libraries. And you do that using this use input sidechain flag or through task operations. Yeah?
So just to make sure I understand correctly, when you say straight from the PDB, as I understand it, that means you basically go through the PDB, and for each amino acid, you ask, well, each amino acid and each protein in the PDB, you ask, well, what is the Rotamer of this thing?
So what I meant by this was that this group had done some data mining, essentially, where they pulled out conformations of the Rotamers from the PDB and made kind of a representative set. And previously we had used that, but we don't use this Rotamer set anymore.
Okay. So what's the difference would be my question.
So the Rotamers that we use are idealized. So their bond lengths and bond angles have been set to ideal values.
After extracting them from the PDB?
Yeah. So the Dumbrack lab, and I don't know the details of how they generated this library, but essentially what they do is they pull out conformations of a given amino acid, and then they bin them in certain ways. And so you have some statistical preference for a certain conformation or another conformation. And that's where our Dumbrack score comes from.
Right.
So how often do you see a specific conformation of an amino acid?
Right. But then they idealize those bond geometries?
Those, yeah. So they've been taken out and idealized, and then binned. The idealized forms of them have been binned. So anytime you make a Rotamer substitution, you're putting in an ideal sidechain.
Okay.
Does that make sense? Okay. The exception to that would be if you have the use input sidechain flag on. And so what is packing actually doing? when we call the Packer, what's happening kind of behind the scenes. And it's a simulated annealing protocol. And so what happens is you start with a relatively high temperature. And so this figure down here is trying to illustrate it. It's kind of inverse what we might think. So here we're trying to optimize, say this is our conformational landscape. And on our y-axis, I should have labeled the axes, but I didn't. We have energy. And so it's reversed because we usually think of minima as where we're trying to go in the energy landscape. Think of energy going this way. So down here is high energy and up here is low energy. So we want to find the highest point on this conformational landscape. That's the goal. So with simulated annealing, what you do is you start with a relatively high temperature. And what temperature allows you to do is accept changes, so conformational changes, Rotamer substitutions, that are of higher energy. The higher the temperature, the more likely you are to accept a Rotamer switch that increases your energy. And so what this, and then as you continue the simulated annealing trajectory, you start lowering the temperature, and this makes it less probable that you accept a high energy Rotamer switch. And so in the beginning, you're able to kind of sample broadly, get out of these local traps, like something like this. So if we wait for it to stop, you'll see that at the high temperatures, it jumps around rapidly. And that's because you're able to accept these higher energy conformations. But as you get to a lower temperature, what ends up happening is that you're less able to get out of these traps in the conformational landscape, and you kind of just drill down into the local maximum wherever you are then, and hopefully that's the global maximum, because at the end of this, you return to your best energy state.
What coordinate did you use here?
This was a figure taken from Wikipedia on simulated annealing, but this is just a general, if you can think of this as, broadly speaking, the conformational landscape, your sidechain conformational landscape. So it's kind of representing the entire set of sidechains on a given backbone for the packing case. Does that make sense? Okay, cool. Great. So how does packing actually happen in Rosetta, and what are the classes that are involved? So the PackerTask is kind of a fundamental part of packing. It controls the degrees of freedom and the options that you have when packing a sidechain. So some of those options are positions that you want to be able to mutate, which rotamers you want to allow, the temperatures you use for your simulated annealing. But the thing about the PackerTask is we rarely touch this class directly. The exception to that would be through a task operation, and we'll get to that. So you usually can configure the PackerTask without touching it directly. You have this task factory generate a PackerTask for you, and we'll go into great detail about how that's actually done. And so that brings us to the task factory. And so this is a factory class that's used to generate and configure PackerTasks. And it works pretty simply by, it has a list of task operations, and it simply applies all of the task operations to this PackerTask, to whatever PackerTask it's configuring. So a lot of the movers that you may encounter in Rosetta that do packing take a task factory, or you can set a task factory. And as I mentioned, a task factory configures a PackerTask from a vector of task operations, and a task operation is just some class that performs a modification to the PackerTask, and it's typically applied by the task factory. And so the task operations are designed to be kind of atomic modifications because they can be linked together through a task factory, or they can be applied on top of one another. Multiple task operations can be applied to a single PackerTask. So with that, we'll kind of jump into more detail about some of these classes. A fundamental part of the PackerTask is that it's commutative. Commutative means that changing the order that you apply these task operations in the case of the Packer isn't going to change the result. You don't necessarily need to, this is done to make things easier, so that if you have a task factory you're passing around, for instance, you can add task operations and you don't necessarily need to be aware of what's already in that. You can safely add a task operation, and it will perform the same as if you had added it first. And a good way to think about the PackerTask is as a statue. This is an analogy I stole from Andrew. And so once you take something away from the PackerTask, you can't add it back. So you're chiseling away some marble. You can't add that back to the statue. You're not going to glue it back on. Once it's gone, it's gone. You need a new PackerTask. OK. So some more basics of what's kind of under the hood with the PackerTask. And this is intentionally brief because, as I mentioned, you kind of rarely deal with it directly. It contains a vector of residue level task, and that's what actually contains most of the mutable settings. So each of the residues in your pose has some residue level task associated with it, and you can access these using the residue task, or if you need to modify them, then the non-const residue task functions of PackerTask. And so you might see these used, but they are usually used by task operations, which are going to be doing the actual modifications to the PackerTask. And some important things to know is that the PackerTask knows the number of residues that you have in a given pose, but it doesn't have access to the conformation directly. And so as we'll see later, the task operation, when it modifies the PackerTask, it gets a pose. So any relationship between the conformation and the residues needs to happen at the task operation level. And if that's not clear, hopefully in a couple slides, it will be. And the default PackerTask allows all rotamers at all positions. And so if you just hand the Packer some pose, it'll allow you to design any conformation of any of the 20 canonical amino acids, let's say, to any position. Yeah.
Using conformation and pose interchangeably?
If I am, then I shouldn't be. A conformation is so pose contains a conformation. And so, yeah, the conformation is what actually has the details of the conformation, as Angie pointed out, so the XYZ coordinates of particular residues and atoms. And so this is useful information for the to control the PackerTask. So you can say, like, pack the neighbors of some residue X. The PackerTask doesn't have this information directly, so you need to configure the PackerTask. So in order to configure the PackerTask with knowledge of that information, you need access to both of those, and the task operation class does. And we'll talk about that in a little bit more detail. So this is an exercise to demonstrate the commutativity of the PackerTask a little bit. So in this scenario, let's say you have some residue 10, which is an alanine, and you want to apply some task operation that says design residue 10 from to a lysine, and it's currently an alanine. And to that same PackerTask, you say also prevent any repacking at residue 40 in the same pose. So that means it can't change its rotamer at all. And then the third thing you're going to do is say restrict every single residue to repacking only. And so that means it can change rotamers, but only rotamers that are of the same amino acid type. And so I'll give you a few seconds to think about it, but what do you think the result of this will be? Which residues are going to be allowed to design, which residues are allowed to pack, and which residues aren't allowed to move at all? Anyone have any ideas?
You said it was commutative, right?
It's commutative.
So you should be able to design a 10.
You should be able to design a 10?
Yeah.
So let me just go to the answer. So the answer I came up with this is that you can't design a 10 because you said here you're going to restrict every residue to repacking only. And so that means repacking only means you're allowed to change rotamers, but you can't change amino acids.
So that takes precedence over? Is it not a matter of precedence?
It's not a matter of precedence. So if we go back to the statue example, we've taken away the ability of design when we restrict residues to repacking.
Oh,
And so, And so we've taken that ability away. And so even though we said explicitly here, we added a task operation that's like design this, because we've already taken away the ability to design, we're not going to be able to do that.
So actually, the first one is, so residue 10 is not even repacked. And the reason for that is that what the PackerTask stores is a list of all the available amino acids that you can change to. And the first command says, make it so that the only amino acid that I can change to is lysine. And the last one is, make sure that I can't change to any amino acid that isn't the one that was there to begin with. And the combination of those two is that residue 10 can't be any amino acid. So basically it gets shut off. It's not repacked at all by the packer, so it's held fixed.
Thanks for the correction. That's a good point. Anyone have any other questions about this example? Yeah.
So is it not repacked because alanine doesn't have any rotamers, or?
So you can actually, well, yeah. So in this case, alanine, because it doesn't have any rotamers. Like at the start. Let's take another example. If that had been a serine to start, then you would have built rotamers for it. Rather, you can imagine building rotamers for serine, but you wouldn't have repacked that serine, so it would have been held completely fixed. And that's because you said at the beginning of the list of available amino acids, start up all 20 amino acids are available, and that gets winnowed down to only lysine, which is not serine. And the last one is nothing except serine at that position. And the combination of those two is nothing. Since you've just like removed all of the marble of your statue.
For that position, yeah.
For that position.
Mm-hmm. Good question. Okay, so this is a little bit tricky, so it's something to be aware of when you're dealing with the PackerTask.
I have a question about that. So, Andrew, do you mean that the reason that you're using alanine and serine, you can design without repacking?
No.
No.
So what I'm saying is that if this example had been that it started as serine, residue 10 was serine to start, and then the first command is say force it to mutate to lysine. That's what I was saying. It's like the counter hypothetical.
It was just to remove the ambiguity here of alanine not moving at all because it has no other rotamers, or because we've removed all those rotamers. Okay. So that brings us to some task operations. They're super useful. There's a lot of them. We're going to go through a couple of them just so you really get the idea of what they're doing. Most of them are defined in core PackerTask operation, task operations with an S there. Task operation without the S is the abstract base class. So that's less useful to you, although still useful. And then protocols toolbox has a task operations folder, and this contains quite a few task operations. And so most of the functionality that you might encounter is that you need the Packer to do has probably been implemented in some sort of task operation. And so make sure you look around before you just go implement something to prevent some duplication of code. And so the task operation base class is pretty simple, and the core functionality is kind of boiled down to two functions: an apply and a parse tag. And this simply allows you to use this task operation with Rosetta scripts, similar to a parse my tag that a mover would have. So apply, as I mentioned before, takes a pose and a PackerTask. And so this is kind of where, so in task operation, because a PackerTask doesn't have access to a pose, and thus doesn't have, also doesn't have access to a confirmation by itself, apply takes both of these. It takes a const reference to a pose, which is so you can't modify the pose when you're applying a task operation, and a reference to a PackerTask. So you can and should modify the PackerTask in the apply of a task operation. That's the whole point, is to modify the PackerTask. And so any conformational dependence that you want to have when setting up your packing run kind of has to be done in a task operation apply, because this is where you have access to both the PackerTask and a pose, and thus a confirmation. And so we'll go through some examples of why this is useful later on. So now we're just going to go through a couple, more than a couple, task operations that I selected because they fit on a slide or they're particularly useful. And so the restrict to repacking is kind of a fundamental task operation that's used all the time, and I kind of alluded to it earlier in that example. So there's restrict to repacking and restrict residue to repacking, and they do very much what you think they do. They restrict either the entire pose to repack only, and by repack only, I mean you can change rotamers within the same amino acid, but not to any other amino acid, so it restricts design. And restrict residue to repacking, which is up here. I don't talk about that, but that is for a specific residue. So you can say residue 10 and 11 you don't want to be able to design, but design the rest of them, let's say. And
Is the packing deterministic?
so packing is
Like if you just do this repack only, like will it converge to the same energy? Repack, or?
So it tends to converge, but it's not deterministic.
So should you generate like an end struct with like 100 or something, or 1,000, or?
It depends on, so the number of rotamer substitutions that you make is dependent on the number of rotamers that are available, which implies that it's also dependent on the number of residues. And it's empirically derived, but, and Andrew can correct me if I'm wrong about this, I think that generally that number is, it tends to converge pretty quickly. So small numbers of trajectories will usually end up with very similar, if not identical, results. Doing like thousands and thousands of packing runs is not necessarily well advised. You can also,
But you should, rather than just repack once and be like, this is the ideal thing, it might be better to generate a couple of decoys and see what the variance in the energy is across them.
Yeah, I think that's a good idea.
I haven't been doing that.
Anything to comment to that, Andrew?
It depends on, you only have so much computer time.
Right.
So maybe you're well suited by doing lots and lots of rotamer optimization. Maybe it'd be better off to do a little bit of rotamer optimization and some backbone modification. So it's not easy to say this for all protocols what the best division of time between, say, time spent in the packer versus time spent out the customer.
Yeah, so it's the best kind of answer. It depends. This is the apply function, just to give you a sense of, this is for restrict to repacking, so not restrict residue to repacking. It just takes the task, and there happens to be a corollary function in the PackerTask, which is restrict to repacking. This happens a decent amount in task operations where the PackerTask has some functionality, and you're just directly accessing through the task operation. But because you have this pose, you can write task operations that do more complex things, and we'll look at a couple examples of those. So this is kind of a very simple and hopefully easy to understand task operation. Initialize from command line is another one of these task operations that simply calls the exact or very similar function from the PackerTask. And basically what this does is allows the PackerTask to be configured from command line flags. And so say you're running fixBB and you give something like extra chi rotamers, and you actually want those to be respected by the PackerTask, you need to make sure that the task has been initialized, accepts initialization from the command line. So if you're running some protocol that you foresee some user using down the line that does packing, and there's not some very good reason for not allowing the user to control packing from the command line, then it's a good idea to add this task operation.
Shouldn't the job distributor take care of it?
The job distributor does not take care of this. The job distributor is kind of completely decoupled from packing. And so the job distributor's job is to figure out what jobs are going to need to be run, generate input structures, because that's kind of like core functionality that we're going to need to do in all Rosetta jobs. But packing is kind of just one thing. You could see a lot of protocols that won't do packing at all.
So job distributor, if we run this through the command line and you pass like Chi1 as an option, it will like parse that.
Yes.
But you're saying
It'll parse.
PackerTask might not know about that.
Yes.
So, that's fair.
Yeah. So like if you in your mover that you wrote the other day made some task factory, added and then gave that to like Pack Rotamer's mover, for instance, which is a wrapper that does packing. Then, so I actually don't know if Pack Rotamer's mover has a default task factory that adds this. It probably doesn't. But if you haven't added this initialize from command line task operation, then you'll ignore those flags. Yeah. Right. Another one that's in a similar category is the ability to read res files. And so this read res file is another task operation, and it'll allow you to set up the PackerTask based on a res file that's supplied from the command line. And we'll go into the details of the res file in a few slides. But again, this is something that's useful to know if you want to add res file support to your protocol. So extra rotamers, generic is a task operation that I wanted to highlight just because it exposes some of the ability to add more rotamers to a rotamer set that's in the PackerTask. And so this extra rotamers allows some fine-tuned control over how many extra rotamers based on chi angles are going to be added to your PackerTask. And so there's some pretty detailed explanation of what some of this does in the options Rosetta.py, which is where all of the options are for Rosetta. If we haven't gone over that yet, I don't think we have. But this is where all of the options that Rosetta can take in from the command line live. So if this detail isn't enough, then I suggest looking there. But just to give you a taste of what some of this is, if you give the flags packing extra chi1 and packing level 1, what this does is it'll add 2 rotamers to residues that have a chi angle, a chi1 angle, I should say, and those are plus or minus 1 standard deviation from the what's considered the ideal chi for that residue. If you find yourself going crazy because you want to do like lots and lots of sampling with extra rotamers, I'll give you a suggestion to try the min-pack mover instead, which places a rotamer and then does minimization on that rotamer before evaluating its energy. And so this is a way of increasing sampling. And the reason I suggest that is because if you add a lot of rotamers to your rotamer set, packing is a combinatorial problem, and so it gets unwieldy pretty quick, and it can take up a lot of memory. As Andrew alluded to before, packing is kind of it can use a lot of memory. It's memory limited. So another task operation, and this is a good demonstration of why the apply function for the task operation takes a pose in. This is called restrict to interface vector operation. And what this does is it disallows packing at residues not identified as being in an interface. So say you have protein A and protein B, and you want to redesign the interface between them. You could use something like this task operation to kind of automatically detect that interface. But say you're writing a protocol and you just generally want to do interface design. If you knew it was going to be protein A and protein B, you could just select the residues that you wanted to be involved in the design. But say you want to run this on 100 different proteins or 100 different conformations of the same protein, that interface could change. And so with this task operation, you can you have access to the pose at that state, and so it can redetect the interface from the conformation. Does that make sense? Okay. And yeah, as I mentioned, it's a good example of why you need the access to the pose in apply. Prevent chain from repacking is another task operation. That's a good example of why you need you might want a pose in the apply. So this very simply prevents a specific chain. It's identified by a number, not a PDB chain letter. So that's something to look out for from repacking at all. So it essentially removes all of the rotamers for the given residues of a specific chain.
Well, why are you emphasizing that this is an example of why the task operation applies?
Because say you have 10 different protein complexes, and the second chain in each of these protein complexes is a different number of residues. So you wouldn't be able to, like if you were just writing a generic protocol, you couldn't say just don't pack residues 50 to 100 because those are the second chain.
Right.
You need access to the confirmation object and say which, give me the set of residues that are specific chain, and then remove the rotamers from that. And I think this is the last one I'm going to talk about. This is a task operation modify annealer that allows you to tweak the simulated annealer that's used during packing. So you can do things like change the start and end temperatures that you're using, or move the quench step. And the quench step is at the end of a packing protocol. You drop the temperature to 0, so you only accept rotamer substitutions that are lower energy. And so this is kind of to drill down quickly into the bottom or top in the example that I gave of whatever well you're in. All right.
Is that different from the multi-cool annealer?
They're different concepts. Modify annealer can modify modifies whatever annealer is being used by the PackerTask, and the multi-cool annealer is one such annealer, simulated annealer. So I put these up here just in case anyone's done with all of the exercises that we possibly put up and it's just breezing through everything, and they are looking for stuff to do that will get them a pat on the back. Not all the task operations have parse tag functions, and so the ones that don't likely aren't compatible with Rosetta scripts. So you could try adding some of those, or if you're interested in one in particular and you want to use it in Rosetta scripts, then you could try implementing the parse tag. If you do that, I recommend adding the documentation to the wiki. That's where most of the Rosetta scripts documentation lives. There's a lot of task operations that function on a specific residue or a set of residues. So for example, restrict residue to repacking, and it might be useful to have some abstraction that consolidates some of this duplicate functionality, because each task operation or many task operations that do this kind of do it differently, and there's a lot of code duplication there. So yeah, those are just some possible things you could explore. All right, and so now let's go into some actual code about how you do control the packer. And the first way we're going to do it is programmatically. So if you're writing some protocol and you have a mover that does design and you want to set up a task factory for it, how would you do it? Usually these movers take task factor owning pointers. And so first thing you would do is generate a task factory owning pointer. And then you'd create whatever task operations you want. And so here we're going to do the restrict to repacking task operation. And then all we need to do is, for the task factory, push back this restrict to repacking task operation. And now if we give this task factory to some task factory aware mover, like pack rotamers mover is kind of a classic example, then it has this task factory and we'll apply it before it makes its call to the packer. Yep.
No, you're just going really fast.
Sorry about that. I'll slow down in general. And we're going to be, I'm sure, doing some of this in some exercises later. So if the details of this aren't clear.
Shared yet, or?
I don't know. I don't think I shared it. Could somebody share that?
Could somebody?
Yes. Could
So you need owning pointers for both the task factory and the task operation.
So the reason we're using owning pointers here is because the task factory's pushback takes a task operation owning pointer, and so we need a task operation owning pointer. And restrict to repacking owning pointer fits that bill. And similarly, many of the task-aware movers, such as Rotamer's mover, take owning pointers to a task factory. So we need. Okay. So now let's talk about res files. Some of you, maybe many of you, have used res files before. They're a pretty intuitive way to modify how the packer is going to do packing and design. And it has some advantages and some disadvantages. It has a relatively simple syntax, which is great. It doesn't require recompiling. Doesn't require any custom code, really. And you have access to a lot of the really common use cases. Some disadvantages is that it's relatively inflexible, in particular that it has no conformational control. And what I mean by that is, like, if you couldn't do the interface definitions of multiple proteins with a res file, for instance. Does that make sense? Might not yet, but hopefully after we go through the syntax it will. And there's some pretty thorough res file documentation. A lot of my examples are going to be pulled from there, and that's in the, there's a link here in the slides, which you'll hopefully have soon. So let's quickly, let's go over the syntax, and then look at a couple examples. And as I mentioned, the full grammar of the res file can be found in the documentation. That can be a little bit overwhelming if you're not used to or familiar with looking at grammars, but there's lots of good examples there too. So it basically boils down into a header section, a line that's says start, and a body section. And the header section is comprised of commands that apply to all residues that are not specifically mentioned in the body. The body is for commands applied to specific residues or residue ranges. And the syntax for that is your PDB num. If you have an insertion code, that would go here, but you don't necessarily need one. That's what the square bracket's for. You can leave that out if you want. And then a command. I don't think this is right. I don't think this should be body. That should be, because that would make it recursive, which is not what we want to do. What was that? Chain. Yeah, that should be chain. And then the command. So sorry for the typo. And this identification accepts wildcards, which we'll look at, and residue ranges. So it's kind of a nice syntax for controlling the packer from the from the command line. So this is an example of a relatively complex res file. So the header is just one line, and it's nat row. And nat row is a command that restricts residues to not packing at all. And so you keep that confirmation. Hopefully it'll be clear at the end of this example why we're using the nat row. And so you start with the head. The nat row means, as I mentioned, no design or repacking at all. And then this first line of our body is star A nat AA. And so for all residues in chain A, we're going to say nat AA, which means keep the amino acid. It's essentially the same as repack only. So keep the amino acid, but allow it to change rotamers within that amino acid. The second line here is for residue 3 insertion code C through residue 20 on chain A. Restrict those to be apolar, and the list of apolar amino acids can be found in that res file documentation that I linked to earlier.
What does 3C mean again?
3 is a residue, C is the insertion code.
Like
It's-
the chain.
No, it's a PDB insertion code, which is different than a chain. They're used a lot in like antibody structures.
Can you clarify real quick?
So I would do a poor job of explaining insertion codes.
Out of like the comma nomenclature or something.
The what?
So there are like some of the antibodies have like a different nomenclature. So that one of them is like a Kabat nomenclature, and what they do is for some instead of going from 1, 2, 3, 4, 5, if you open the PDF in any viewer, it will say 1, 2, 3, 3A, 3B, 3C, 4, 4A, something like that. So it's just considered as a different numbering. Instead of just going from 1 to 100, it will be less numbers in the end, but there will be like 3, 3A, 3B.
Is that because the PDB has different, like they built in different rotamers? That's the decision, or it's just the total?
Basically, if
Oh.
you make an alignment between
Yeah.
the structures, sometimes the alignment doesn't match. Sometimes you have gaps and sometimes you have extra registers in different regions, and so that's why you have the insertion code to account for that.
And so
you
the
could
residue
basically-
20 would always refer to like some part of the antibody, like scaffold.
Mhm.
Whereas like, I'm just making this up here. Residue 15 or 15A, 15B, 15C would be like one of the loops.
Okay. Okay.
So the loops
To maintain like
size-
canonical numbering.
Okay.
Right.
But that
Mhm.
way, so you'd have like a whole bunch of insertion codes for one of these loops that change the
Oh,
size.
all right.
But residue 20 is sort of in the same place.
So you're saying that this residue 15 has two different flavors to it? Is that?
They're actually different. They're different residues.
Oh, they're different residues?
Yeah. So like you could have like residue 1, 2, 3A, 3B, 3C, 4, 5, 6, 7, and those are. It's not the same as like having like some PDBs have alternate conformations.
Right,
That's different.
Different.
Mhm.
Because when I read this on the wiki, I actually I didn't ever use the syntax, but I thought it meant starting from residue 3 on chain C.
Gotcha.
Residue 20 on chain A.
No, that is not what it means. Yeah.
Okay.
And what if you hit like, there's an insertion event into all of this?
Mhm.
Okay.
Yeah. Cool. So this would go from residue 3C to residue 20 on chain A, and and restrict them to apolar residues. And then, and as I mentioned, the set of apolar residues can be found on the wiki or on the documentation. And then the last thing is residue 15 on chain A. You're going to pick the amino acid tyrosine, and so that's force designed to tyrosine. And so, what is all this going to do? Well, it's useful to start with the most specific thing first for res files because they don't have this same apparent commutativity that like a task operation would. So this can be a little bit confusing. The most specific thing is what determines what is allowed for a specific residue. So residue 15, chain A, pick a tyrosine, sets residue 15 on chain A to be tyrosine. Even though we said all this apolar, NAT-AA, NAT-RO stuff before, because this is the most specific, it's going to happen. The next most specific thing is this residue range. So it sets all the residues between 3C and residue 20 to be on chain A to be apolar. And then going even slightly more general, this is all the other residues on chain A that are not part of this range and are not residue 15 they stay at their native amino acid but can change their rotamer within that amino acid. And then every residue that wasn't specified, so every residue that's not in chain A, essentially for this example, is kept to be your native rotamer. Yeah.
I'm confusing it because
Okay.
I thought you're talking about like that statue, right? You're like Michael,
Yeah.
You're like Michelangelo, right?
Uh-huh.
NAT-RO, it means you have to keep your native rotamer.
Yep.
So how can you then go back and at position 15 pick a different amino acid?
Yeah, and this is confusing. There's a discrepancy a little bit in how you configure the packer between task operations and res files. Res files are parsed all at once, and so they kind of have access to all of the information, and so they have this convention of applying the most the restrictions for a given amino acid are determined by the most specific command that contains that amino acid. And so there's a discrepancy, and it's a confusing discrepancy between
So how
the
you
example.
interface with the packer is not the same as how you write a res file. Like the two are not.
Say that again?
How you would interface with the packer.
How you would apply task operations,
Apply
yeah.
task
Mhm.
operation.
is different than how you might generate a res file, and that's confusing.
That's confusing
Yeah,
to me.
understandable.
So the res
So
file.
the deal is that the PackerTask has this commutativity requirement, right? So that if you call a function in the PackerTask, if you call two functions, then it doesn't matter what order you call them. That doesn't apply to anywhere else in Rosetta, right? So it's kind of like the difference between, say, like close and score function. You just say, well, they're just different things. They have different rules they operate to. And so the res file, it has its behavior, and but it's gonna, the res file reader is gonna interact with PackerTask, but it's only gonna, it's not gonna call functions that would override each other. It's gonna make sure that when it calls functions in PackerTask, that it's not going to both say nat row and aka tyrosine. It's going to be one of those two.
The packer.
This read
The res file.
task operation will do one of those two things, but it won't do both.
Oh.
Right? Because the PackerTask says everything's commutative.
Okay.
The read res file, read res file task operation. It's not. It doesn't have to behave commutatively, right? According to its input file, it can behave however it would.
Okay, so then it's in read res file where it chooses what commands to apply to each residue.
Yeah.
Yeah, so read res file has some
Awesome.
relatively complex logic that prevents it from, that allows you this functionality.
So if I understand how this works,
Mm-hmm.
it has some kind of ordering of how specific
How specific a given command
it
is.
does,
Mhm.
and then it orders them in that order, and then it asks pretty much, have I set some rule already that would contradict this previous rule?
Yeah.
Don't set that.
Mm-hmm.
Is that kind of the gist of how it works?
Yes. It's not even that contradicts this rule necessarily. It could be like, let's say if this was apolar and this was all AA or something like that. I guess those do contradict. Yeah.
It could even be something like
Trying to think.
orthogonal, like saying I want extra
Yeah.
rotamers
Okay.
at everything on chain A. I would also mutate residue 15 to tyrosine.
Right.
Okay.
Tyrosine doesn't get extra rotamers.
Yeah.
Gotcha.
It doesn't get the command that's applied to everyone else. It only gets its own command.
Correct.
So once it was set with something, it can be set with something else that's less specific?
That's true. Yeah. Mhm.
Okay.
Now you can have lots of instructions on that 15A line.
Right.
Yeah.
Say-
So if you wanted extra rotamers here,
Okay.
and for every residue, you could put them up here and here. It would be silly to put them up here because you have this nat row, so it's not going to repack any of them, so you're not going to have extra rotamers.
PackerTask kind of made sense. I just find this like unintuitive.
I can understand where you're coming
I
from.
don't know if it's just me or not.
So res files are pretty powerful. They let you do a lot of the general case, but as I mentioned, they don't allow you to do things like neighbor detection or anything that's confirmation dependent. Yeah.
So to simplify, would it be like rules and exceptions? Would that be a way to simplify how this works?
I'm not sure what you mean. Can you elaborate a little bit?
When you say native rotamers, and then you specify for a particular residue a different rotamer or a different residue. So you have a general rule, but you have an exception that takes precedence over the general rule.
Yes. It takes precedence. Yeah. And as Andrew was saying, even if that not only takes precedence, but even if those two are completely orthogonal, only the more specific one gets applied. Mm-hmm. Cool. Any other questions on the res file?
I have a question.
Yeah.
So at the other level, you could use use input sidechains.
Uh-huh.
So you can still do this with res file. Do you assume that you use the input sidechains?
You don't assume that you use the input sidechains. Use input sidechain is a command that you can put into a res file.
Okay.
And so for a specific amino acid or for all amino acids, you can use a specific sidechain. You use input sidechain, I should say. Okay. And so the last way I want to talk about controlling the packer is through Rosetta scripts. And as I mentioned earlier, in order for a task operation to function in Rosetta scripts, it needs this parse tag functions, a parse tag function, I should say. And this is a really minimal example just to get it to fit onto a slide. But in Rosetta scripts, you have this task operations block. And here you can define an arbitrary number of task operations that have a name and other input that's parsed during the in the parse tag function. So in this example, we're using the restrict chain to repacking. We're calling it ch1 repack, and we're restricting chain 1. And then later on, when we're setting up our movers in Rosetta scripts, we're gonna create a pack rotamers mover and give it task operations, a task operation or list of task operations. This is a comma separated list. So if we had other task operations, we could add a comma here and add those there as well. In this case, we just have one. So we give it chain 1 repack. And then in our protocols, we add that mover in pack. It's called pack, so we add that mover named pack. And if we were to run this protocol through Rosetta scripts, then we would repack, but chain 1 would repack only. It wouldn't be allowed to design. And other chains, if there were any in the pose, would be allowed to design.
So here you're taking a task operation called restrict chain to repacking, and you're passing it to the pack rotamer.
I'm creating a task operation
Okay.
called restrict chain to repacking.
And then you're giving it to the pack rotamer's mover?
Yes.
Okay.
Mm-hmm.
Okay.
And so behind the scenes here, a PackerTask is made of this task operation, and it is given to pack rotamer. Cool. Any questions about this? So this is kind of maybe one of the more verbose, but one of the more powerful methods of controlling the packer from the without having to recompile, but still having access to some of the conformational niceties that task operations allow. Yeah.
So the chain numbering is obviously not PDB numbering.
Right.
Generally not the case in Rosetta, or where does it primarily fit?
It's not the case in the conformation object of Rosetta. Those are chains have numbers in the conformation object. You have access to you do have access to the PDB chain within a pose. It's in a PDB info object. I don't think we're going to go into much detail about the PDB info object this week, but there's some general, there's some useful information in that.
Okay.
Mm-hmm. Okay.
Not all poses come from PDBs.
Yes, that's true.
You can construct a pose from a fast sequence.
So some things to keep in mind that I mentioned already. Packing is a combinatorial problem, and thus the addition of extra rotamers through like extra chi, for example, can increase runtime and memory usage dramatically. The packer stores rotamer pair energies in an interaction graph. Andrew's going to go into detail about this later, so I'm not going to say too much about it. But suffice to say that lots of rotamers can lead to lots of memory. And Andrew might mention this later on. If memory is becoming an issue, I'll let him deal with that. Okay, so that's packing in Rosetta. Now we're going to move on to some more fun stuff. Internal coordinates, degrees of freedom, and the FoldTree and atom tree. So a lot of you are familiar with what internal coordinates are. And basically, it's a way of defining the position of an atom based on the properties of its connections to the surrounding atoms. So this is the way that we think of chemistry a lot of times. You think of bond angles and bond lengths and torsion angles, and those are all internal coordinates. And so this is a really natural way to think about protein structure, and is the way that it's a natural way to think about changing protein structure, but it has some repercussions that you need to be aware of if you're dealing with an internal coordinate system. Great, so this is just a figure that I stole that's showing some of the internal coordinates of phenylalanine in this case.
Why do you need to? I thought the whole power of internal coordinates is that you don't specify reference frame, right? You don't have to give a Cartesian coordinate.
You don't have to give a Cartesian coordinate to a particular atom, but at the root of at the root of your there needs to be a Cartesian coordinate somewhere. It's the first atom must have a location defined if you ever want to have a Cartesian coordinate for any of the other systems in the network, because in the system. Does that make sense? That was not a particularly clear answer.
It sort of does. I just thought, okay, I mean, it's more of a philosophical point, I guess.
Okay. We're going to go through this in more detail, and hopefully it'll clarify some things. So some consequences of movement in internal coordinates is that you can have this lever arm effect. If you have some peptide chain and you make some torsion change over here that's relatively minor, you could have a pretty dramatic change on the other side of your chain. Another important consequence is that if you do change the Cartesian coordinates of an atom, let's say, you are changing the internal coordinates implicitly. And if you do this and the internal coordinate that you change is not being scored by the score function, then you may never know that you did something really awful to your system. And so an example of this would be, say, if you moved some atom in a phenylalanine side chain, you would be allowed to do that, or you can figure out a way to do that within Rosetta. And even though that's completely non-physical, let's say you move it somewhere else, we don't have a that's not necessarily true. By default, we don't have a score term that will penalize this crazy conformation now you have for this phenylalanine, because it's not a degree of freedom that you would normally change. It's not an internal degree of freedom that you would normally change. Is this making any sense?
First part, I don't understand your second.
Okay.
I don't understand your third point.
Gotcha. Hopefully this will be, if this.
Are you talking about inside of Rosetta, or are you talking about
I'm specifically, and I should have mentioned that this is, I'm talking about Rosetta because you have a score term, you have a score function in Rosetta. And so what I'm trying to warn you is that if you make changes that are to either internal coordinates that are not scored or Cartesian coordinates that change internal coordinates that are not scored, then you may not know that. It won't necessarily score this poorly.
How would you make such changes?
You
have to call a method where
you might have to do it intentionally. If you have some specific reason why you want to do this, it's just be careful if you're thinking of doing something like this.
Why wouldn't it be penalized though? I mean, say if you move an atom and you get a new internal coordinate, it's still somewhere in the scope of the energy function, isn't it?
It depends on what you change. Like for instance, Andrew mentioned with a proline, which has a ring back to the backbone. You can change that you can break that by changing torsions. And so we have this by changing backbone torsions. And so we have this score term that makes sure that penalizes if you've broken this imaginary bond in the atom tree. But like if you did something to a side chain, like a phenylalanine side chain ring that broke the ring, we don't normally think of sampling the degrees of freedom that you would change by doing that, the internal degrees of freedom. And so we don't have, there are some score terms that will, but by default they're not on.
So that's a specific case where you originally thought, all right, nobody's going to mess around with the phenylalanine ring.
Yeah.
And if somebody does,
Yeah. Okay. So the core kinematics library is how Rosetta is where Rosetta defines all of its internal coordinate information. And the three classes I'm going to talk about in this library are the atom tree, the FoldTree, and the MoveMap. I'm going to kind of gloss over the FoldTree because we're going to go into it in more detail in the afternoon tutorial. So the atom tree is responsible for keeping the internal coordinates and the Cartesian coordinates synced. The FoldTree is a residue level representation of the atom tree, and it's convenient. Well, convenient is a stretch, but you can work with it. And the MoveMap is a class that allows easy controlling of the degrees of freedom that you can sample in, say, minimization. So let's talk first about the atom tree. Atom tree is, as I mentioned, responsible for syncing internal and Cartesian coordinates. And this is a lazy syncing process, and so the coordinates aren't synced until they're requested. And as I mentioned before, it's rare that you need to access the specifics of the atom tree directly or change the atom tree directly. You usually do it through the use of a FoldTree. And as a tree, there's some important properties. It can't contain cycles is a very important property. And so Andrew talked about this before. Conformational cycles, like in a phenylalanine or like in a proline, are technically, they're not cycles in the tree. And so you need to constrain those with score terms if they're going to change.
The more like disulfide you have in your system, the more the energy is going to be off, because you have to add restraints to keep those. Right, you're adding energy and to keep the cysteines from.
Yeah, I don't know what you mean by the more the energy is going to be off.
Well, I mean you have to add more restraints to keep the cysteines pointing at each other, for example.
You need to add score terms that will penalize them not being together,
Right.
for sure.
Yeah, that's what I mean by adding energy, or adding score, whatever, adding the score function.
Yeah. So you will certainly need to do that for protein structure. But the number of them, I guess I'm just a little confused by when you said that the more you have, the more your energy is going to be off.
No, because don't you have to have more? You have to have a restraint, right, for every disulfide bond.
And we restrain things through score terms.
Right. So the more disulfides you have,
the more times that score term will be invoked. Yeah.
Okay.
Mm-hmm. Or have a zero score. Okay. And so let's talk about some of the concepts that are inherent to the FoldTree. Probably the most important one is this concept of a stub. And a stub is a local orthogonal coordinate frame defined for every atom in your system. And so stubs are how you map internal coordinates to Cartesian coordinates. And in Rosetta, an atom is always located at the origin of its own stub. And the Cartesian coordinates, the Cartesian location of a stub's origin, which is the atom's position, is derived from its parent stub using spherical coordinates. That's a little confusing. We're going to go through an example of that. And a stub is typically defined by three atoms. And I have a really simple little demo of how this is kind of done. Jack Snoyek, who was going to get talk on Friday, gave me these cool Zoom tools. And so this helps me conceptualize how you create a stub from let's say, three atoms. And so the first atom is going to be the origin of your stub. The second atom that you give, let's say, is here at the end of this. We'll call this a bond. This defines the xy plane. And so when you take the cross product of, so you have 3 atoms. The first atom is your origin of the stub. Your second atom defines your x-axis. The vector from the first atom to the second atom is your x-axis. Let's say that's here. And so this is our x-axis. And the third atom in the system defines this plane. And so if we take the cross product of our first bond and our second bond, that'll give us our z-axis. And then if we take the cross product of these 2 vectors, that gives us our y-axis. And so that's how a completely orthogonal system is generated, or coordinate system is generated from 3 atoms that you'll give it in pose. And so those are that's how we define stubs in Rosetta. You give them 3 atoms, and the atoms that are used are in the params file, and Andrew went over a params file earlier. So you can find the atoms that define a stub in that file. All right. Another concept that I want to talk about is jumps. And jumps are just like stubs, but where jumps relate where stubs relate an atom's internal coordinates to its Cartesian coordinate, a jump relates 2 internal coordinates to one another. And so they're used in Rosetta to separate chemically separate entities. Like 2 chains are going to be separated by a jump in Rosetta.
Jumps and stubs are both atom tree things? Or?
They're both atom tree things, yeah. Okay, so here's some figures that I made for internal coordinates. And this is how you would go from your parent stub and some spherical coordinates to your position, and thus the origin of your own stub. And so in this lysine, this atom right here is our parent. We're going to try to place this nitrogen, let's say. So from our parent stub, that's the origin here. Let's say that this stub is defined by this residue, by this atom, and this atom. So the x-axis is going to be defined by this bond here, and we'll call this x for a crazy reason. And the y and z are going to be defined in the way that I mentioned with the Zoom tools. So you have this orthogonal coordinate frame now here, so now to generate where your position is, you need 2 things, the 3 things in the spherical coordinates. You need the distance from the origin to this atom n. You need theta, which is going to be the angle between the y-axis and it's going to be this angle here. And this is somewhere in the xy plane. And then phi is going to be your torsion around this. And so this is the rotation around your x-axis. So theta is a rotation around the z-axis. And phi psi rather, is a rotation around the x-axis. And from those 3 pieces of information, you can place your position. And then this position becomes the stub origin for the downstream atom.
So which 3 atoms? You use the nitrogen and the 2 carbons?
In lysine, I think that the stub for this nitrogen is here, here, and here. So it's the 3 atoms that are before it.
It's a 3 carbon. Oh,
I'm sorry. The parent stub is those 3 atoms.
So it's those 3 carbons that allow you to get the position of the nitrogen.
It's the coordinate frame defined by those 3 atoms, and the distance and 2 angles in spherical coordinates that get you this nitrogen position. So in order to get a position of any atom, you need your parent stub and then these 3 parameters: distance, theta, and psi. And so these are the atom level degrees of freedom that you have. Actually, it's just science data.
But typically should be a right-hand coordinate system, right? Because you're showing the left-hand line.
Yes.
Oh, what was that? That's fine.
It's
So X, Y, Z.
the X and Y are in the wrong place. Yeah.
Where Z belongs going into the board.
Right.
Right. Sorry about that. I'll fix that. Okay.
Where is the distance criteria kept?
Where is the distance criteria kept?
Yeah.
The distance between atoms.
It's not a constant distance, obviously, right? I mean,
Right.
it depends on the identity of the atom.
So it depends on. So the atom object stores the conformation. Stores the XYZ coordinates of a particular atom, but also the internal coordinates, if I'm not mistaken. No, where is that stored?
It's in the atom tree.
It's in the atom tree. It's all in the atom tree. That makes sense. Yeah. Okay. So that information is stored in the atom tree.
All right.
Yeah. Okay. And so refolding, which Andrew talked about earlier, refers to the updating of Cartesian coordinates when internal coordinates are changed. And so you only need to do this in the example I had with my hand before. You only need to do this if you only need to update the coordinates that are downstream from you in the tree. And so the way this works in Rosetta is you keep a list of all of the internal degrees of freedom that you've changed, and then you find the minimum set of nodes that you need to change downstream of, and then you propagate through those changes and figure out update your Cartesian coordinates based on your new internal coordinates. This happens a lot. Okay, so that's the atom tree. The FoldTree is a residue level representation of a molecule that can be used to generate the atom tree. And the FoldTree is easier to work with because it's a little bit more conceptual, and we're going to go through a detailed example of that in the afternoon after this. Okay, so that was my brief introduction to internal coordinates, and now the last thing we're going to do is talk about controlling movement. Specifically, we're going to talk about the movement, the MoveMap, and then some common ways you modify a pose or move a pose. A brief aside, I want to talk about core ID because I kind of use some of this stuff in the upcoming slides. Core ID holds classes that are used to identify some Rosetta concept. And so examples of this would be the atom ID class stores a residue number and an atom number, and that uniquely identifies an atom in your system. A torsion ID class uniquely identifies a torsion, so it has a residue, your torsion type, which can either be backbone, chi, or jump, and then the number of the given type of torsion within this residue. So like phi, psi, and omega would have 1, 2, and 3, for instance. That's so torsion is a number, and those are all backbone torsion types. So so the MoveMap has this hierarchy of degrees of freedom, and so there are residue-based degrees of freedom and atom-based degrees of freedom. The residue-based degrees of freedoms are your backbone, chi, and jump. The atom-based are this phi and theta that we talked about when we looked at the atom tree. And then there are 3 different levels that you can kind of specify degrees of freedom at. There's at the entire system level, so all residues or atoms in the system, and there's a single residue, atom or jump, and then there's a specific degree of freedom. And so this is there's a representation of each of these in the MoveMap class. And when you specify a degree of freedom, all the settings that are lower in the hierarchy are going to be cleared out. So as an example of that, let's say we set a specific torsion ID. So a torsion ID is the most specific setting we can have. It's the residue, the type of torsion, and the torsion number. So let's say this is a specific phi that we're setting to be movable in our MoveMap. So we'll set that to be true. And then we go and set something that's a little less specific. We're going to say all the backbone torsions of residue 4 to be true. So this allows all the torsions at residue 4 to be true, but clears our DOF, our specific settings. So if we had set for the torsion ID 4 phi to be false here, it would be set to true. And then the most general level is at the entire pose level. And so you can set an entire torsion type. So let's say all backbone to be flexible. And this will clear residue level settings and degree of freedom specific settings. Okay, so taking a step back and going into some more practically useful things, I'm going to just discuss a couple different ways that you can move a protein in Rosetta. Packing, we talked about already. This is the common method of how you change the sidechain information, but also change the conformation of those sidechains. And so really all we're going to talk about is some of the fundamental ways you can incorporate backbone movement into a protocol. Some discrete backbone moves are small and shear. These are kind of the most basic operations you can perform on a protein backbone. They're implemented in protocols. There are implementations of them in protocols, simple moves. There's backbone mover, which is an abstract base class that small mover and shear mover are derived from. A backbone mover you can perform lots of these moves in one apply, and you can do things like check your Ramachandran score for any angles, any new torsion angles that you come up with from these moves. And so a small move modifies the phi psi of a single residue, but doesn't. So as I mentioned before, the lever arm effect. If you do this, you can pretty dramatically change anything that's downstream kinematically or downstream in your FoldTree. When you do this, a shear mover modifies the phi of residue I and the psi of residue I minus 1, and it does this in such a way that it attempts to minimize this downstream propagation of this change. Yeah.
Which backbone mover does Relax have?
Relax does. I'm not sure Relax does small and shear moves at all.
Classic Relax does both. Fast Relax does not.
So Classic Relax does small and shear. Okay.
Yeah.
Classic Relax is a lot slower and not much better.
And would you say which one?
Fast Relax.
Fast Relax is which one?
Neither. Fast Relax ramps the repulsion term. So you start off with the low. Okay, never mind. Might talk about that.
Get to?
I have no idea. Tomorrow. We're going to talk about it. Okay. Another discrete backbone move you can make is the back rub move. This was a move that came from the Richardson group at Duke, and they noticed that this type of thing happens in high-resolution crystal structures. And so this is the rotation around an axis defined by the vector between two atoms, and it was originally observed as the axis between the C alphas of residues that are so if there would be one residue in between these, so between I and I plus 2. if you do a vector between their C alphas and rotated it around that slightly, that would be the back rub move. And this can change some of the other. So this is one of those things that if you weren't looking out for it, if you did this rotation, you could change some internal degrees of freedom or some internal some coordinates that you may not be scoring. The back rub mover handles that. It's aware of it, and so it tries to minimize its effect on those. And I'm not exactly sure how that works, but you could read the paper, which I don't give a reference for here. And this is a completely local backbone move, and is defined in protocol's back rub mover. And then the last thing I'm going to talk about is fragment insertion. So if you're familiar with Rosetta at all, you probably know that it does some fragment insertion. So this is kind of how it got its name in the protein folding world. And fragment insertion is a pretty simple concept that you apply torsions to a given pose that are taken from some fragment of naturally occurring protein structure. And so you have some library of fragments that you can pull torsions from. Historically, these fragments were 3-mers and 9-mers, but you can use any size you want with the new with the fragment infrastructure that's in Rosetta. And it's another way of sampling realistic groups of fine psi angles for a stretch of amino acids. All right, I think that's all I have today. So I may have finished early. Did I finish early? So now we're going to go talk about, we're going to do a tutorial on the FoldTree. And hopefully, yeah, we're going to do that first.